Good day and welcome back to part 3 of our discussion on differentiating the trig functions. In the previous two videos, we've built up to and developed the differentiation formulas for the trig functions. And what we saw is that using the definition of the derivative of sine is cosine. And a similar argument can be used to show that the derivative of cosine is minus sine. And once you have the derivative of sine and cosine, you can use the quotient rule to get the derivative of the remaining four trig functions. The derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is minus cosecant cotangent. So as I mentioned at the end of the previous video, these are certainly formulas that you need to know in the sense that you can apply them as they arise. One quick reminder is that when it comes to differentiating the cofunctions, cosine, cosecant, cotangent, those are the three formulas that involve a negative. And it is worth reminding you, if you forget one of these formulas other than the derivative of sine and cosine, you just go back to that quotient rule. So even if you don't remember, say, what the derivative of secant is, you could use the quotient rule to calculate that, fairly quickly and efficiently if needed. So now that we have these formulas introduced, what remains is working through some of the common examples that we would expect to encounter. So the first type of problem is simply differentiate some function involving trig functions. And in this case, when we see something like the derivative of secant times tangent, the product rule needs to be applied. So the product rule would tell us what? The derivative of the first times the second plus the first times the derivative of the second. And this is where those differentiation formulas come into play. The derivative of secant is secant tangent, and then we're multiplying it by a tangent. And the derivative of tangent is secant squared. And most definitely you could leave the derivative in this form. If you wanted to simplify it a smidge, you could note that a secant pulls out of each term, and then you would have a tangent squared plus secant squared left over. But I would leave it exactly in this form. The second question or example we have is another familiar type of problem. One of these, find the equation of the tangent lines at some point. So let me just give you the quick reminder. When it comes to finding the equation of this tangent line, we immediately know the desired form. It will be y is equal to f prime of 0 times x minus 0 plus f of 0. So as usual, that leaves us with two values that we need to determine. What is the function value at 0? And what is the value of the derivative at 0? So let's go ahead and just do a couple quick computations. So in terms of the function that we are dealing with, we have f of x is x over 2 minus tangent of x. So f of 0 would be 0 over 2 minus tangent of 0. And just to make sure that we're all on the same page, what is tangent of 0? And hopefully you're saying 0. So we end up with 0 over 2, which is simply 0. So we've determined the first function value that we need to find, f of 0. The second function value we need involves the derivative. And to differentiate this function, we should use the quotient rule. So what I'd recommend is pause the video and finish up this problem. You have all of the key ingredients that you need. It's just a matter of one more computation involving the derivative. Okay, and hopefully at this point you've paused the video, you've finished up the problem, so let me bore you with a few of the details. So when we differentiate using the quotient rule, we think low, d high, and now I'm going to just start writing out what those derivatives are. So d high would be the derivative of x, which is 1, minus high d low. And when we differentiate the function 2 minus tangent x, we'd get back 0 from differentiating the constant minus secant squared. And this is all divided by the bottom squared. And if I want to know what f prime of 0 is, I could now just simply substitute in x equals 0. So I would have 2 minus tangent of 0. And note above minus a minus becomes a plus. But it's kind of irrelevant once we plug in 0, right? So 0 times secant squared of 0 all over 2 minus tangent of 0 quantity squared. But it's worth just the reminder here. You know, we've already said tangent of 0 is 0. What is secant of 0 equal to? Secant of 0 would be 1, so secant of 0 squared is also 1. And just note, if there's any confusion, secant of 0 is 1 over cosine of 0, and cosine of 0 is 1. So what we are left with in the top is 2, and we're dividing by 2 squared. So 2/4 is 1/2. So this is equal to 2 over 2 squared, which is 1/2. And putting this together, we now have the desired equation of the tangent line. Y is equal to 1/2 the quantity x minus 0 plus 0, which is maybe more conveniently written as y equals 1/2 x. And these are two examples of common problems involving differentiation, regardless of the type of function that we might be dealing with. Let's look at a slightly different question that's maybe more specific to dealing with some of these trig functions. So something that we could ask, what is the 23rd derivative of the sine function? And let me just first pause a moment with notation, since we haven't encountered this. So in terms of notation, for differentiation we might think f prime, f double prime would be the second derivative, f triple prime would be the third derivative, but after a while, the more derivatives we have and the more kind of primes or dashes we have representing them, it becomes a bit cumbersome. So once we get up to that fourth derivative, we will represent the number of derivatives that we want to take as a number in parentheses. So note, if it was a fifth derivative, it would be a 5 in parentheses. So in general, we're thinking if you have f raised to the power n in parentheses, this is our notation for representing the nth derivative of f. So let's go back to our example and see if we can calculate out the 23rd derivative of sine. And hopefully we won't have to calculate all of these, but let's just see what happens. We start off with our function f, which is sine. We can differentiate sine to get f prime. That's cosine. And if we wanted the second derivative, remember that would be the derivative of the first. And we said the derivative of cosine is minus sine. So far it's all familiar ground. The third derivative is the derivative of the second derivative. So when we differentiate with a negative sign, that remains. And then the derivative of sine is cosine. And if we keep going, we say, okay, the fourth derivative, we differentiate again. So we would have a minus times the derivative of cosine, which is another minus. So note the minus, a minus cancel. But once you get to that third derivative when you differentiate, you just go back to the starting point of sine. So there's this cyclic behavior that we're seeing. And I think there's a very convenient way to represent this that will help us now with derivatives, but it will also help us later on in the semester when we get to things called antiderivatives. So how I remember this cycle is tangent is sine over cosine. And then I add in the opposite functions, minus sine, minus cosine. And if we go around in the clockwise direction, each arrow represents taking one derivative. That is to say, the derivative of sine is cosine. If we wanted to differentiate sine twice, we'd go 2 arrows, so minus sine. A third derivative would be minus cosine, and so forth. And note, every multiple of 4 in terms of derivatives gets you back to that starting point. And we can now hopefully very efficiently answer the question that's been asked. What is the 23rd derivative of sine? Well, every multiple of 4 brings us back to the starting point. So sine would actually be the 24th derivative of sine. So if I want 23 derivatives, I need to go back 1. So the 23rd derivative of sine is minus cosine. And to make sure that we really see what's going on with this example above, I want to ask us to calculate one more derivative, just for fun. What is the 1007th derivative of minus cosine? And note, I'm purposely picking a really large number. I've had the experience in the past where I may have chosen something smaller, like for example, what's the 17th derivative? And I'll have a student write out each and every one of those derivatives all the way up to the 17th derivative, which certainly works, but it's also not all that efficient time-wise when we can think about it this way. So I think 1007 is large enough that you're not going to write them all out. So using the idea above, pause the video, see if you can determine what is the 1007th derivative of minus cosine. So hopefully you've paused the video and you've taken a few minutes to think about this. The cycle that we have above, still applies. If we start off with minus cosine, each one of these arrows going in the clockwise direction is going to represent a single derivative. So every 4 derivatives that we take gets us back to this starting point of minus cosine. So we just think, what's a multiple of 4 close to 1007? And the answer is, well, 1008. So if you were to calculate out the 1008th derivative of minus cosine, that would just be minus cosine. So 1 less than that would leave you at minus sine of x. So the 1007th derivative would be equal to minus sine x. And note, this is specifically for the function minus cosine. So that completes the examples that I wanted to cover in this video. The next video will pick up with a few additional examples and get back to some of those common limits that we introduced previously. So stay tuned and take care.